Thank you, thank you. Thank you so much for being here. I bet there are repeaters. So this is our third engagement here at the 92nd Street Y. If you 2 years ago, we started this with a night on this nature of consciousness with Antonio Damasio and David Chalmers. Last year, we had one on the nature of faith with Rebecca Goldstein and Alan Lightman. And tonight, we have something on immortality and or mortality, because obviously you can't think of one without the other. So in order to do that, I thought that it would be very interesting to have a conversation on the different scales in which we can think about the problem, right? So we can, of course, think about it from a human scale. Now, we are all animals that have this very perplexing dilemma that we are self-aware and that we know that our life in this planet is of a limited time. And so we have this combination, I can say like this superposition of two tendencies which tend to be quite different, which on the one hand, we are animals, we have hair and nails that grow, we reproduce like mammals, most mammals do, and yet we can conceive of the infinite, we can think about transcendence, we can think about change and transformation, and we know who we are. At least we know we are alive and we have an understanding of what that means, right? So in 1973, the cultural anthropologist Ernest Becker wrote a book which won the Nobel Prize, the Pulitzer Prize in 1974, called Denial of Death. And in this book, he explores precisely this issue, right? How do we find meaning knowing that we have these two extremes pulling us somewhat apart, the animal nature, the demigod kind of nature, right? And it's a very complicated conversation. And at about the same time, in the 1970s, the first models of climate change were being developed. And the realization that there was a human impact on the weather was becoming more and more obvious to those who were studying this. So you can think of mortality or the extension of life, immortality, from a human scale to a planetary scale. And tonight I am incredibly proud to have two leading thinkers on these topics, Siddhartha Mukherjee and Elizabeth Kolbert. So let me introduce them and they'll join me here on stage. So the way the night goes is essentially like this. So each one of them will talk for about 15 or 20 minutes. Then we will talk amongst each other. I'll ask them questions. They may have questions to one another for another 15 or 20 minutes. Then we're going to open for Q&A from you, okay? And there is a procedure for that. I think you have cards or something like that that you write on. I don't know exactly the details. And then we are going to address your questions. And then after that, we have a second part to the evening, which are more informal. Basically, we go backstage and not back this way, but back that way, into a room where there'll be some drinks, as far as I understand, and there'll be an opportunity for us and for you to talk at a different kind of level, not from stage to audience, but from the same kind of level. Be sitting next to you and we can have this conversation together. If you have other questions that weren't addressed during the official time, so to speak. Now, let me ask you something. You hopefully got a survey as you came in. And to us, because this is a grant-based program, right? I got this grant to promote this connection between the humanities and the sciences from the Templeton Foundation. I need to show them that people care by answering the survey. So please, if you want this to happen and keep happening again, hopefully next year again here for our 4th year, please do fill the survey and somebody will be collecting that on the outside. All right, so without much ado, let me introduce our two speakers. So Elizabeth Kolbert has been a staff writer at The New Yorker since 1999. Her 3-part series on global warming, The Climate of Man, won the 2006 National Magazine Award for Public Interest, among other honors. She received a Lennon Literary Fellowship in 2006 and a Heinz Award in 2010, and won the 2010 National Magazine Award for Reviews and Criticism. She is the author of The Prophet of Love and Other Tales of Power and Deceit, Field Notes from a Catastrophe, which is now available in paperback. And finally, The Sixth Extinction, for which she won the 2015 Pulitzer Prize for General Nonfiction. So everybody, please welcome Elizabeth to the stage. Elizabeth. Thank you. So you go, I think, all the way to the other side. Yeah. And then I have Siddhartha Mukherjee, who is a pioneering physician, oncologist, and author. A very influential voice in the scientific community. He is best known for his books, The Emperor of All Maladies, a biography of cancer, which earned him the 2011 Pulitzer Prize, and The Gene, an intimate history, which was recognized by the Washington Post and the New York Times as one of the most influential books of 2016. The Emperor of All Maladies was adapted into a documentary by Ken Burns and included among Time's 100 best nonfiction books of the past century. So Sid, please join us. Thank you. Okay, very good. So we're going to start, and the first one to speak will be Sid tonight. So Sid, take it on. And
well, thank you very much for picking such an easy topic.
I know.
To start with, small, moderate topic. I thought I would begin with a thought experiment, and the thought experiment goes like this. If you were sitting in the 1850s, you asked the question, what is it like to get old? What is it like to live beyond 50 years old? Someone might say to you, it was a horrible life. Your teeth fall out, your hair degenerates, your skin degenerates. It's a terrible thing, and what we should really do is respect human boundaries and dignity and let people die quietly at 50. Fast forward a few years, and all of a sudden those realities, your skin degenerating, your hair degenerating, your body, your mind falling apart, starts to change because all of a sudden we begin to make important advances, scientific advances, cultural advances, advances in public health, hygiene, when all of a sudden 50 isn't a boundary. And that same person who told you, why not just give up at 50? It's a terrible life out there. Would start saying, well, actually now 60s sounds good. And so on and so forth, 60s become 70s. So there are two strands in our understanding of longevity of the body. One strand constantly reminding us that death and aging and the end is nothing but inevitable, and that's of course true. But on the other hand, another strand pushing and saying, well, what's inevitable about it? What is it about? Certain organisms live much longer. There's no, what are the biological limits? Well, the biological limits are defined by what we want to understand and how we want to push them. So I think that there's, as a physician, as an oncologist, as someone who works in cancer, you feel both these strands. And it's important to remember that the two strands exist. Absolutely true. It's absolutely true that there is a kind of collapse of dignity when you begin to say, let's all live till 100, and that changes and distorts certain ways of thinking about culture. But on the other hand, let's not forget that, as I said, 100 years ago, people would say living beyond 50 was a horrible life. So with that as a kind of background, I thought I would propose to you three potential visions of longevity or immortality. And they're quite different from each other, and each one has a very different consequence about how we think about human future. The first one is the most traditional one, and that's the one that we've grown up with in a kind of cultural sense. And that's simple. It's immortality viewed in the negative or in the double negative, and that's simply if you killed all the killers, you would achieve infinite longevity, or at least true longevity. This is the stuff that I came into my sort of professional life, my scientific life, take diseases away. remove cancer, heart disease, and other such diseases, infectious diseases in the last so-called, if you look at human history, it's an astonishing history in the last 100 years because the conquest of communicable diseases, so-called infectious diseases, lengthened human lives, human longevity, whether that conquest was through public health measures or however we achieved them, a mixture of things, mostly public health and hygiene, some vaccination, of course, some use of antibiotics among those things. That changed the epidemiology of human disease. Most of us would be dead in this audience. We would be all long gone 100, 120 years, odd years ago. Virtually none of us would be here, actually. And then the epidemiology, the face of human disease began to shift and become more and more focused on these so-called non-communicable diseases, so much so that it feels these days that the division of the world between non-communicable diseases and communicable diseases, infectious and non-infectious diseases, is a little bit like saying mammals can be divided into cows and non-cows. That's because the category of non-cows, non-communicable diseases, heart disease, cancer, even in countries that you wouldn't imagine, even in parts of the world where you would think that the burden of communicable diseases is enormous, the pattern is shifting so dramatically that there's an expectation, for instance, in a country like, just to pick one out of the hat, Tanzania, more people will die from the complications of hypertension than they will die of the complications of various infectious diseases in 10 years. That's one kind of. So this gives you a sense of the changing nature of epidemiology. But to go back to the question, if you kill all the killers, if you remove the constraints or the barriers to long life, that you would actually increase human longevity enormously. And of course, there's a truth to that. But then came a second vision, which began to appear, and it comes from a variety of sources. And I'll talk about the sources. It turns out that if you look at people who have extreme longevity, people who live 120 years, 118, 108, 110, what's interesting about those people is that they are not killed by killers. They, in fact, are dying from diseases that we don't think of as diseases. So they, for instance, die of peculiar forms of bacterial sepsis. Their immune system collapses. They sometimes die of broken bones. My laboratory, actually, we study bone. We found stem cells that make bones. There's this project that we're doing right now to try to find people with extreme longevity, to ask the question, what happens to stem cells in their bone? We discovered these stem cells some years ago. We're trying to put them back into human beings. They make bone and cartilage, among other things. So the second idea is that, sure, you can take away the killers, you can kill the killers, but there may be changes that prospectively, outside removing the killers, there may be genetic or biological, epigenetic, or other changes that would allow us to extend human longevity without focusing on the killers. So in other words, there are genes or diets or bionic mechanisms by which you could alter your lifespan in a positive way. So imagine I would find a gene in a small animal that increases longevity enormously. And such genes have been found. Interestingly, many of them have to do with the way we regulate metabolism. Many of them have to have there's a very careful balance between those genes and the capacity of them to tip into cancer. And so there's a very, very tricky balance, but occasionally you can find genetic means of changing the limits of human longevity. And one interesting consequence that arises out of that is to say, well, forget about killing all the killers. Maybe we should be tampering with human genomes so that we can increase longevity. I would say, we were talking about this a little bit before, in trans, which means that they suppress all the other effects. They would override any other effects, and it would be non-disease specific. It's not as if they would essentially override the effects of diseases. And do such genes exist? Yes, they exist in other animals. They exist in worms and in flies. You can make worms that live 3 times longer than other worms. Often these genetic means cluster along pathways, along very particular ways. Often they cluster on metabolic pathways. And for a long time, you would imagine that these alterations, unless all of a sudden there appeared a genetic mutation, a genetic variation in humans that would spontaneously arise and that could give that kind of longevity, you would imagine it would be very hard to tamper with this physiology. But certainly you can tamper with the physiology in other animals, worms, as I said before. And now, one thing we'll talk a little bit about, with new genetic tools, it's possible to tamper with the human genome in principle. And when you do that, again, remember, you can do it in 2 ways. You can remove you can remove constrainers, and we'll talk a little bit about that. But also you can change in a positive direction. You can not just remove the constraints, you can influence in a positive direction, just like in small animals. And here the world splits into, generally speaking, 2 kinds of camps. One camp would suggest that longevity and all these complex traits are so complicated that there'll be many, many genes, and possibly across. So just to give you a sense of what the scope of the problem is, if you were to take the human genome and you were to print it out in standard print format, it would be about, a single human genome would be 66 full volumes of the Encyclopedia Britannica. So this room, wall to wall, up all over, would be Elizabeth's genome. And in the past, of course, it was largely inscrutable. So it's written in just 4 letters. It would be, if you opened up one volume, it would read ACT, GC, TT, TGC. That's not, I'm making it up. I didn't memorize the sequence. But so in the past, our capacity to read that information was extraordinarily limited. You could say in volume 36, on page 72, I have a genetic sequence that encodes for the cystic fibrosis gene. And if you change this letter to that letter, you can go from a normal cystic fibrosis gene to an abnormal one. And if you have 2 copies of that and so forth, then you could make some conclusions about it. So these were single genetic changes which we could map onto human traits, diseases, and so forth. Now we are getting to a place where we're actually beginning to read this information in a powerful manner. I call this reading. Just to give you a sense of how powerful that can be and how disruptive that can be, I just read a paper 2 weeks ago, still in preprint, where they took human height as a characteristic. Now, height's a very interesting characteristic because we know it's highly heritable. Tall parents tend to have tall kids. Shorter parents tend to have shorter kids. This was known for a long time. But for decades, people had been trying to find so-called a gene for height, single genes for height. And for most human variation, they were very hard to find. And we knew that there were probably tens of thousands of variations. There are only 20,000 genes, but the lettering is very wide. So there were tens of thousands of human variations that would explain, ultimately, each with small effect, that would explain height. The problem, of course, was that in order to decipher that, you would have to create a compendium of all human beings and all their heights, find all their genome sequences, and try to find a machine, a computer or an algorithm that would correlate one with the other. And there was not, all of these resources didn't exist. But it turns out now they do exist. And this particular paper uses a powerful computational algorithm to predict human height from genetic information alone. Take away malnourishment. That's a very important constraint. This is assuming no malnourishment, assuming no environmental change. We'll come back to that in a second. From human genetic information alone. Now, think about that for a second. That means that in principle, you would be able to predict the height of your unborn fetus before that child was ever born. You would know what height they would attain. And now think about extending this potentially to other attributes, color of hair, the color of your skin. And all of a sudden, you've gone into territory which I think all of us would feel a little uncomfortable with. Longevity rides along similar principles. We don't have fundamental notions about it, but it will be very, very clear that the heritable part of longevity, the part that can be inherited, will begin to be solved. In fact, that's a project going on right now. This is one of the great biobank projects, so longevity. So then we will be able to read longevity, and if there are genes which very strongly influence longevity, or if there are genes that very strongly influence longevity in a negative direction, we can potentially change those. There happens to be one already, a big candidate, a gene that increases your risk for neurological syndromes, Alzheimer's disease, neurodegenerative diseases, called ApoE. And someone like George Church and others have made a compelling argument. Why not take it away from the human genome? Why not remove that? Why live with this constraint if you don't have to live with this constraint? So that would be the second vision of longevity tipping into far edges of mortality. It's not immortality, but far edges. And then the last one is perhaps the most intriguing one. I've been thinking about this as a thought experiment for a long time and wondering, and the question that I posed myself a while ago was, could there be a soft version of immortality? Could we hack it? And by that I mean not inventing crazy new tools, but what if someone gave me the toolkit of what's available? Could I make a kind of soft immortality possible? And I began to think about the following experiment, thought experiment. And I'm going to write more about it because I've been thinking more and more about it. So let's say here's the thought experiment. Let's say I used you, Elizabeth, as an example. We are quite confident that we could clone you. You can clone most mammals. It's not easy, but within limits, I think the possibility of cloning is becoming more and more clear. And if it's not cloning, we could even do a soft version of cloning in which we would derive sperm and eggs from your normal cells, combine them, and basically recreate a soft version of a clone. So it wouldn't be the Dolly version of the clone, which is more complicated, in which you have to take another cell out, suck up the nucleus and re-inject it with your nucleus, thereby creating a clone. We could do it a bunch of different ways. You could recreate basically sperm and eggs in principle from someone's cells and then combine them again. So let's assume for a second that we would be able to do the cloning piece of it. And then here's the experiment, which is that what struck me was that the cost of digital recording of all your experiences is diminishing so dramatically that you could basically wear a GoPro and walk around. And you could edit your GoPro. You could edit your GoPro as you aged, and you could say, these memories were really significant for me. You know, that time I went to Rio and sat on the beach, that moment I experienced that glacier, etc. So my question was, what if we began to clone ourselves and then give our clones the capacity, and this is not even fancy technology, I'm not talking about brain interfaces, I'm just saying give them a GoPro. Give them a quick GoPro lesson on your life, in which they would absorb and perhaps even experience what you thought were the fundamentally important pieces of you. So you would have yourself in a second generation now absorbing pieces of you. What's interesting about the experiment is that it's infinitely repeatable. Your clone makes a clone, gives a GoPro to the clone, et cetera, et cetera, et cetera. And of course, information is lost. It's not going to be your life. But I just keep wondering about this idea. It kind of haunts me a lot. I mean, what if I would do that? Would it alleviate some concerns that I have about my end? I would end, but very important pieces of me would be left over. A genetic copy would be left over. A true genetic copy would be left over. And, things I treasured, my most important memories would be here. So anyway, it's dystopic, of course. But, yesterday's dystopias are tomorrow's old news. So there's a quality about this that makes you think. This is a thought experiment, but makes you think about. And then the question, of course, becomes, well, what happens to human population then? Right. How do we crisscross? So I'm going to stop there. That's kind of a broad introduction, but those were my three visions of longevity tipping into the edges of immortality.
That's great. Thank you very much. And now we go for the macro view.
Yeah, speaking of dystopia. So that was like a perfect lead-in, and I am supposed to, I guess, represent the humanities here. I'm up here with two scientists, and the humanities always are, get the short end of the stick, the bum end of the stick. And so I'm gonna talk about, Sid talked about immortality, and I'm gonna really flip that around, and I think that there is a really interesting conversation. It's not a conversation. Maybe it's something much worse than that. How's that? We can a brawl. And that is, I'm going to talk about what humans have meant to the rest. That we don't really know how many species exactly there are on the planet. The rough estimates are about 10 million. We have named maybe 1.5 million of them. So there's a lot of life out there that we sort of know from statistical tools are out there, but we really don't know what it is still at this point in 2018. But we know that we're destroying it pretty rapidly. And the reasons for this have a lot to do. They're the flip side of our tremendous success at staving off disease, at reproducing, at feeding ourselves, all the things that have brought us to the point where there are now 7.6 billion people on the planet, heading very rapidly. We'll hit 8 in the next couple of years, actually. And if you want to know exactly, you can go, there's like a world population clock, and you can watch that thing spin around by the, not just by the 1 or 2 or 3, but by the 10,000s, every few minutes, as our population grows. So what are the, so I wrote, I wrote this book about this idea that we are causing a mass extinction. So what is a mass extinction? A mass extinction is a very simple concept. It's just considered a period of time, a short period of time, relatively short on a geological scale, when a lot of the diversity of the planet, for whatever reason, crashes. And this idea that there's a sixth extinction obviously implies there have been 5 previous ones. There have been, lo and behold. The first occurred 440 million years ago during a period known as the Ordovician period, when life was still largely confined to the water. So about 3/4 of all marine species died out, and very few on land, because there were very few on land. And the most familiar one of these mass extinctions is the 5th, which did in the dinosaurs 66 million years ago. And there's a pretty broad scientific consensus now that one was caused by an asteroid. And for a long time, people tried to find common themes in these extinctions. Is there one reason why they happen? They happen at irregular periods, and no one has found yet, the key, what causes a mass extinction. But the general sort of theme of them is that the world changes in some way faster than evolution can keep up with, right? So it all does boil down to genetics. So if I'm a worm or a plant, I can only keep up with environmental change by either I have enough plasticity, and I have enough adaptability. If I can't go here, I go there. If I can't use this food source, I go that food source. So all organisms have a certain amount of plasticity. But the other way I adapt, I make big adaptations, is through mutations, through evolution, right? I evolve, I become a new creature, and that's propelled life throughout the last 3.5 billion years or so. So if things change really fast, and I don't have the plasticity, and I can't evolve fast enough, the end is near. That's the end of the line for my species. And what are we humans doing we've sort of transcended evolution in a really, really important sense. And this gets to a lot of the things that Sid was talking about. We don't wait around to evolve, right? If we have a new pathogen, when you go to get a flu shot, right, that flu evolved into a new virus, but you got the vaccine and you skipped that evolutionary step, right? So the flu didn't just kill off everyone who wasn't immune to it. We jumped over that, and that's why we've done so well, why we've extended our own lives, why we're so successful. But the flip side of that are these massive changes that we are making to the planet on a geological scale. I'm sure everyone in this room has heard this concept that we're in a new geological epoch, the Anthropocene. An epoch is actually, to a geologist, a very small amount of time. There are many people who believe we're in a new geological period. So, and we're in the, what are we in, the Neogene or something like that, but we may be in a whole new period of time, a very big geological divide, because we're changing the planet on such a scale and at such a rate and on such a scale. So I'm just going to throw out a couple of the ways we're doing that. Unfortunately, I could spend all night talking about how we're doing that, but I will not. I will turn this over to a conversation. We're changing the climate really fast. We're putting up CO2 really, really fast into the atmosphere, perhaps as fast as has ever happened in Earth's history. And when you think about it, it makes sense. It's really hard to put CO2 into the air, right? So all the fossil fuels that we are burning are just carbon that a plant absorbed during its lifetime. The plant died, and for complicated geological reasons, didn't decompose, but became a fossil fuel. That process took hundreds of millions of years, and we are now digging up those stores of fossil fuels. We're burning them, let's say, in a matter of a couple centuries. So that's really, really rapid, and if people weren't here, how could that be happening? We're acidifying the oceans. That same CO2 that we're throwing up into the air that's changing the climate is changing the chemistry of the oceans. We are very rapidly altering the surface of the Earth when we go in, to the Amazon, or when people came to the U.S. and mowed down the prairies and planted corn. That's a monoculture. That's a place where very, very few creatures can survive. Everyone's heard about, monarchs are crashing, monarch butterfly populations. That's because, we go in to what used to be their habitat. We just mow it down, put down herbicides, plant corn, and there's just nothing for them to eat. It's as simple as that. Other ways, we are moving things around the world. This one doesn't get as much attention as it probably should, but over the vast span of evolutionary time, the continents have divided. All the continents used to be squished together about 250 million years ago into a continent we call Pangaea. Then the continents split apart. The world as we know it came into being. Evolutionary lineages have been evolving separately for tens of millions of years, and then we bring them together, right? You go to Africa. Someone from Africa comes here. You go to Asia, vice versa. We're moving goods around. We're moving people around. We're moving viruses around. We're moving fungi around. And just to give one really local example of what happens is people have probably heard of a white nose syndrome killing bats all across the U.S. That was a fungal disease, fungus brought over from Europe, probably totally unwittingly by someone that's just killed millions and millions of bats. So oftentimes when people try to date when did the Anthropocene begin, they use one date that is used as the beginning of the use of fossil fuels, and another is post-war when the human population really, really took off. So all of these questions of what we're going to do to enhance our own lives, unfortunately, are coming at the expense of all these other species with whom we share the planet. And that is, I unfortunately have come to believe, a pretty inevitable conflict, because there's only a certain amount of space and there's only a certain amount of resources on planet Earth. And then, just to bring things full circle, and then I'll hand it back over to Marcelo, there's going to be all these questions. Well, we killed off this, we killed off that. Can we bring it back? Can we use its genome? We now are so sophisticated. We can just take, people have mapped the genome of the Neanderthal. Can we recreate a Neanderthal, right? Just reprogram a human cell to be a Neanderthal, or an elephant cell to be a mammoth. Those questions if we're all around in a technologically advanced society like today's, 100 years from now, which I'm not 100% sure of, are going to be very, very urgent. And we'll be debating them very, very heatedly. So with that, I'm going to...
That's great. Thank you very much.
So, Elizabeth, so maybe this GoPro clone thing is not so bad. You just get one.
You just get one yourself.
Yeah, so one of yourself.
I say,
no
kids, just,
kids,
okay,
right.
shrinking population.
Shrinking population,
Yeah, well, look, we could combine forces, yeah.
Exactly, exactly.
So I think that's great because you kind of nailed it. There is a clear tension between these two narratives here, right? On the one hand, there is science as the conqueror of all maladies, including death, viewed perhaps as a disease that can be cured in some way, right? And let's do that. And I have a somewhat very visceral aversion to scientism, the idea that science actually has answers to all questions, because it does not, for sure. And it's highly debatable, I think, if death is something that we can really deal with for many reasons, even invoking physics and the second law of thermodynamics. I mean, in the sense that every time you solve a problem, every time you kill one of the killers, other killers show up, right? I mean, this has been, you're one of the best historians of medicine around, and you know this is true. And the question is, can this ever end? Or is this just part of the way life manifests itself, right? But there is this idea that science has the hero. And then on the other hand, as you said, there is the other narrative, which is destruction. We as a species, in order to be so many and in order to live well, the first thing we need is energy, is environment, and that obviously has a tremendous cost, right? And to me, and this is a question I have for both of you, it's because I have no idea how to answer that. When you talk to people about these things, and I'm sure you both have, I mean, Elizabeth, when you talk about the Sixth Extinction and you put data in front of people and you discuss this with educated people and they understand it, but they don't change, why not? To me, that's mind-boggling.
Well, I think unfortunately, the more, one thing I want to say too is that this is maybe not really an answer, but people have been at this project for a really long time, this overcoming of evolution, and I think there's, it would be called debated, but most, I think, scientists, once again, I'm going to defer to scientists, would say, humans did in the megafauna. The megafauna extinction was really early on, so humans arrived, in Australia 50 or even 60,000 years ago. There was a wave of extinction of large animals. They arrived in North America, probably 15, 20,000 years ago. There was a big wave of extinctions. We no longer have, mammoths or mastodons running around New York, though we have plenty of skeletons of them. So, it's not something that, it's a project I think, unfortunately, we've been at a long time, and it's just that our tools have gotten a lot better. And now when you think about the pace of change right now, right, your iPhone, everything has been collected from somewhere on the planet and has had an impact somewhere on the planet. And so, the changes that are required when you have 7.6 billion people on the planet, even if you just said everyone is simply going to, needs to eat. That's basic requirement, these sort of basic human rights. And these things come into, really serious conflict pretty quickly. Now, if you said, let's do our best, our absolute best, we would like everyone on the earth, to have a decent life, and we would still like to preserve as much of the rest of the planet as possible. Sort of the best proposal I've seen for that comes from E.O. Wilson, and he has a book called Half Earth, that we should sort of put aside half of the land surface of the Earth aside for other creatures. And I think that's a really important idea. But it turns out, a multinational project like that, it's really, really hard to even get it talked about.
Of course. Yeah, I think it's something to do with the amount of pressure that people respond to at the individual level, and unless there is enough pressure, the threshold you haven't gotten to that threshold yet, and you will not do anything. You won't take shorter showers. You won't, eat less meat, whatever it is, even if you know that there is a cost to all of that. And it's an interesting reflection to understand what will it take for people to do something, not at the governmental level, but at the individual level, because we have power as customers, and I think there is a whole emerging idea of corporate ethics now, where some corporations are beginning to understand that, hey, if you don't like a company, you stop buying their products, and they have to change. And so, you have some companies that you wouldn't expect getting organic products out there and stuff like that. But it's just a reflection that I think we should have. And in this conversation, you can always interrupt and ask questions to one another too. I don't want to monopolize. I have a ton of things I would like to ask you both. Okay, I'll ask you now, Sid, something about this discussion about the ethics of gene manipulation. Where are we with that conversation?
So, well, let's talk about the technology first, and then let's talk a little bit about the ethics of genetic manipulation. Again, the background is this reading and writing paradigm. So remember, we are now becoming progressively, particularly with computational powers, becoming progressively able to read, make sense of this encyclopedia, 66 volumes of the encyclopedia. And then comes the question of writing. And for a long time, as many of you know, the writing piece of it, changing the human genome prospectively, which would be essentially saying, go to page 66 and erase the word, ACTT, and change it into CCTT. And that might mean changing a gene like a mutation in the breast cancer-causing BRCA1 gene and making it the non-breast cancer-causing so-called normal variant or the wild-type variant. That was that project was very badly stuck for very good reasons. So the reasons are very deep and biologically very deep. So the biologically they're deep because, as you can imagine, any time you take information away from any genome is a cellular crisis. Cells are extraordinarily sensitive to their genomes being tampered for a good reason, because when that happens, the consequences are usually quite severe. Cancer is one of the major consequences, that a mutation that eventually causes cancer. So cells, we're now knowing more and more. So we've discovered some of this in our lab, and other labs many labs have been working on this. Cells are extraordinarily sensitive to these kinds of changes. And in general, they were very hard to deliver. The wormhole, and again, this goes back to taking control of evolution, rapid control of evolution. The wormhole came from a very unusual place, and it was not expected. The wormhole came from bacteria, the microbial world, and it came because of evolution. It came because in the microbial world, the resources are often so restrictive, and there's a constant cat and mouse game between microbes to compete with each other. So in the microbial world, what happened many years ago is that some bacteria began to be invaded by viruses. We've reconstructed all of this, by the way. We don't know if this is true. It's mostly reconstructed. Bacteria began to be invaded by viruses. Viruses are parasites. You can think about them. They use the bacterial cell to make more copies of themselves. They're not living in the traditional sense. They parasitize the bacteria's body, its genetic apparatus, et cetera, to make more copies of itself. That's what a virus is. So we knew all this, but what we began to understand is that bacteria have a counter-evolution mechanism. And they evolved a mechanism, basically, to detect the DNA of the virus and make a cut in it, chop it up. And the field sat there for a long time. This idea that scientists began to recognize that some bacteria could have a recognition sequence. They could recognize a virus sequence and deliver in a directed chop, not to any other part of their own genome that was protected, it was specific for a sequence. And I'm going to rephrase exactly what I said. In other words, the bacteria could recognize ACT-CC-GTTT and chop that section, ACT-G-CTTT. Now, obviously, if you think a little bit ahead, you could say to yourself, well, if the bacteria can do that, what if I re-engineered the bacteria, put it into a human cell, and now said, instead of going and chopping the virus, why don't you go chop the human genome? ACT, as far as the bacterial apparatus is concerned, it can't tell whether it's a virus or a human genome. It has no fundamental mechanism to tell. And in fact, that's what has happened. In the last 5 years, we have co-opted this bacterial immune system, which is an antiviral system, to chop up or to be directedly go to page 66 in the Encyclopedia Britannica of Humans and go and make a directed change in the human genetic material. Now, human cells haven't given up. They are still protesting. They're saying, no, wait a second, I'm not ready. And sometimes they shut themselves down. So we're now, but the technology is extraordinarily simple. Because I could tell you that it would take a postdoc in my laboratory to make a directed genetic change in a human stem cell. It would take on the order of weeks to months. It now takes 2 days. And virtually all of them work.
And this is CRISPR?
This is CRISPR,
But
yes.
I have a question. So, but once I had an infant or an adult, right? I can't change all of their cells, right? So I have to go at the moment of conception in there.
So there are three. So this is a very important question. So there are 3 kinds of changes, and we should know about all 3 of them. So one of them is making changes in all other organisms. So this is using CRISPR to make modified crops, modified animals, et cetera, et cetera. There you would change, presumably, the sperm and eggs. Actually, you won't change the sperm and eggs. You would change the stem cells that make sperm and eggs. And the big debate there, now we're coming back to your essential question, the big ethical debate there is the debate about diversity, biosafety. That's the central debate. And this, of course, goes very much into what things that you think a lot about, Elizabeth. The second one, the second arena, broad arena, is making changes in human cells, but not in sperm and eggs, as long as they're non-sperm and eggs. So like blood-forming stem cells, like stem cells that make pancreas, the stem cells that make skin, etc. I'm using the word stem cells because you make the change and you let the cells propagate the change in the body. So there, the big safety is concerns about possible consequences in the person that receives the cells. The biggest one of them being cancer, basically. That, the second, number 2, and number 1 and number 2 are already being done. We will find the first CRISPR-based therapies in the next, we are working on them ourselves actively. We will find them in the next 5 years. Changing human stem cells using CRISPR-like technologies is here. It is now yesterday's news as far as science is concerned. The human experiment needs to be done. We don't think that they will cause cancer in the sense that people are worried about. Maybe there'll be some. So this is a very active area, lots of debate around this. The third one, which is obviously the most challenging one, the one that's most debated, is making changes in sperm and eggs, or rather stem cells that make sperm and eggs. And if you take that, the third arena, this is different from all the other 2 because this change is permanently heritable through the human genes. This is a prospective change. Technologically, there's no fundamental reason it cannot be done. And the most surprising piece, and then I'll stop, the most surprising piece that's emerged in the last 3 years, at least to me, is that we had thought that big groups were put together, National Academy and National Institute was put together, a conference. We had thought that they would say absolutely not for human genetic change. In fact, what they said is for diseases that have extraordinary suffering in humans, that we should be allowed to explore this arena for human beings. That was the first recommendation. This will change. This is an evolving conversation. But that was a big line in the sand that we are going to be able to cross. We're going to say that for diseases that cause extraordinary human suffering, potentially a gene like ApoE, we should be able to make a prospective genetic change in human sperm and eggs. This is a wide debate. This is not going to close tomorrow, but that's where we're sitting right now.
it's interesting that this is, I think, the 200th anniversary of the publication of Frankenstein.
Uh-huh.
Which was a cautionary tale precisely about, how far science can go without messing things up big time, right? Because, everybody watches the movie, but if you read the novel, and I can't see you right now, but I wonder how many would raise their hands saying, did you read the novel, And the novel is about the monster not being like Mr. A.B. Normal in the brain, but actually being a genius, having the brain of a genius, and begging the doctor, Victor Frankenstein, for a companion, a female companion. And then when the doctor realizes that his experiment first worked, and second could create a race of monsters which are much more powerful, stronger, and brighter than humans, he panics, and hence comes the drama. So, the reason why I bring this up is first because you have to in a night like this, but also because imagine that we get there, right, that we can do this. And, you can put as much legislation as you want, in scientific practice, but it's a bit of a Pandora's box. Once a scientific idea is out in the world, you just can't put it back in. And there will be groups that will be doing it for the wrong reasons, right? And some groups will be doing it because they can pay to do it. And so, because the therapies may be very expensive, and so you start having a sort of unevenness in society of those that can take advantage of that and have their kids be super smart, super beautiful, super etc., and those that can't. And you go into the Brave New World scenario. Right?
Yeah, but just to temper some of that. I mean,
Yes, please temper it.
There are many. Just to temper it very clearly, as I said, there is a substantial camp of people who correctly believe that tampering with human and animal genomes is going to be fundamentally restricted by the fact that typical traits that we want to influence are run through tens of thousands of loci in the human genome. And changing, and you cannot use CRISPR in that sense. You can't tell CRISPR, you get into a numerical problem. You can't tell CRISPR to change tens of thousands of, CRISPR evolved, as I said, to make very directed changes in very directed loci in the human genome. Now, there is a smaller other camp that says that's not true. It says that, sure, there could be tens of thousands of variations in the human genome that influence a single trait, but somewhere along, either that you could create a synthetic gene completely outside a biological, known biology, or there's a natural gene variant which will override all of this. We were talking about overriding genes. And we've seen examples of that. I'll give you one great example of that. Height is controlled by tens of thousands of loci, maybe hundreds of thousands of loci across the human genome, and yet one gene, like the Marfan syndrome gene, can override many of these and cause extreme changes in human height. I can give you several other examples of this. This second camp believes that there'll be more examples of that. And in fact, perhaps the most challenging example is that in animal studies, we now know that maze-solving cognitive abilities of animals, it's a very poor measure ultimately, but some things capture some cognitive ability of an animal, again, controlled by tens of thousands of genes. And yet, actually, only a couple, by influencing 2 or 3 of them, you can get a maze-solving animal genius. So if you now translate that into the human world, you all of a sudden get, so let me, just to temper a little bit, there are camps out there. I would say the latter camp is a minority. The former camp that believes complex human variation is going to be tough to tackle using these mechanisms is a majority. But maybe, Elizabeth, I'll ask you a question about that. What do you think about bringing back biodiversity using these new metrics or new? Are you enthusiastic of that, or are you?
Yeah. Well, it's like all roads lead to George Church, who has spoken, a Harvard geneticist who has spoken about bringing back a mammoth. That actually Asian elephants and mammoths are quite closely related, more closely, I believe, than African and Asian elephants, and that we could just, we could rejigger an Asian elephant and get a mammoth. I think that there are a bunch of things to be said for that. Besides, let's just assume for a moment that we could overcome the hurdles, which are great, because as soon as an animal is extinct and dead, recreating its genome becomes, extremely difficult. But let's say we have an animal, we are driving it to the edge of extinction. We take a live animal, we just, sequence its DNA, pretty easy to do right now, bank it, and then we decide let's bring this animal back. There's a lot of questions you have to ask. One is, why did it go extinct in the first place? So you're not gonna be able to. A lot of animals, if it's been being done in by a disease, if it's being done in by a predator, an invasive predator, for example, you put them back out there, you're just gonna have the same problem all over again. So you gotta deal with that. But I think a more profound question, and this actually gets back to your clone with a GoPro, is what is identity, right? So there's a case right now, and this is not sci-fi at all. It's a very simple case of conservation biology where they had a species of the Hawaiian crow, got down to really, really low numbers. It's a distinctive species from our crow here in the continental U.S., considered sacred by Native Hawaiians, down to like 20 birds. They did all sorts of things, set up a breeding facility, you double clutch birds, you take the eggs, the birds will lay another egg, you raise the bird by, people raise the bird, blah, blah, blah. You can do all these things. They brought it back to a point of having maybe 150 birds. Just recently, put some of them back out in this forest, which they very carefully, tried to get rid of predators, blah, blah, blah. And it's killed, the first ones were killed by hawks because they didn't know how to defend themselves from hawks. They hadn't been trained. So, an animal is not just a collection of genes. We know, the more we learn, there's a lot of culture.
Crow needed a GoPro.
Exactly. Crow. Well, there you
Parent
have it.
crow needed a GoPro. Transmit to this.
Exactly. But I'm thinking about my
Go crow.
clone doesn't want to watch my memories. It's not interested in my memories. And I actually have clones. I have identical twins, so I have clones. And I always wanted them to write about, I am a clone, but they never wanted to do it. But they're actually very different people. They've had very similar experiences, and they have, identical genetics, not epigenetics perhaps, but identical underlying genetics, and they're still very different people. So I'm not sure I see the point of all that.
Yeah, well,
That was not a question.
well, I know, because to a very high extent, we are defined by our memories, and the clone may look like you, but it's just a thing, it's not you anymore. And of course, if you go talk to real transhumanists, they're going to say, no problem, in the future, we're going to be able to store the essence of your consciousness in a digital program, and as long as you back it up, you're going to keep having it. So you can always reimplant it in the brain of your clone.
Now, this is what I was saying. This is my soft version of it.
This is exactly. So this is GoPro Plus. But
Exactly.
anyways, we have to move on because we have to have some questions here from the audience. Here goes. So how was that? I think that's for you, Sid. How was in vitro fertilization perceived at its advent? Do you anticipate that using CRISPR to modify embryos will eventually become as acceptable to society as IVF is now?
So that's an important question. So, when in vitro fertilization was first conceived, it was conceived as a mechanism to get over a terrible burden, which was infertility and the capacity, people's desire to have children. That was the original driver for that. And so, what's interesting about it, as you very well know, is that it moved from, and it has remained very much in that arena. But it also it becomes also enabling technology, even though it wasn't. And this I'm trying to make a general principle out of this, which is that although it was invented for the purposes of solving an illness, it became enabling technology. It has become enabling technology for prospective genetic change that may not have to do with illness. And by that I mean that because the egg is outside the human body, you can do things that you couldn't do in the human body, including things that I just talked about before. You could do selections for different, and that, interestingly, has nothing to do with CRISPR, right? So that only has to do with reading the genome. So if you can read the individual genomes of in vitro fertilized embryos, you can select one versus the other. And in fact, many of the proponents of many of the people who've think about genetic change say that as far as constraining the field of human genetic or genomic changes, that's enough. That's sufficient. Unless you want to make changes that are introduced into the human genome, things that are entirely foreign to the human genome, you don't need to do very much. You can, by embryonic selection, you can achieve virtually anything that the CRISPR mandate of extraordinary suffering has to do. You can remove any forms of extraordinary suffering, given constraints, just by that technology alone.
Okay, Elizabeth. So how optimistic or pessimistic are you with respect to the future of humanity in a planet that is changing so fast?
Well, I mean, I think that humans, precisely one of the complexities here is that we are so adaptable and so clever and such great tool manufacturers that we are, thinking of, mucking around with the genetics of everything on Earth, for just to name, one of an infinite number of examples. So, optimistic, pessimistic, I think it really gets into, are we going to do ourselves in? Quite possibly. We've had the capacity to do that ever since, Robert Oppenheimer said, I am death, the destroyer, or whatever. So that's, now we're going on, over more than 70 years, right? When were the first Trinity tests? So, and that's not a very long time in the history of the planet to have a capacity to destroy the planet. So the fact that we haven't done it yet doesn't make me that wildly optimistic. But yes.
But there's a moral syndrome that's building around not tampering with human genomes. It's not clear to me that there should be a moral syndrome around not tampering with genomes.
No, I'm not really not arguing.
What's the morality? Why should we not? I mean, I can.
Why shouldn't we tamper with the genome?
Well,
of every.
Again, again, remember this argument came, and I'm talking about genomes in general. Remember, this argument came before a panel. The CRISPR argument came before a panel. And it was, the most vociferous people who argued at the panel were patient advocates, people whose children are affected with terrifying diseases, women with. So I just want to be just to sound a note that yes, it sounds, we'll destroy the environment, et cetera, et cetera. But there is also, on the other hand, I mean, I think it's fair to say that scientists aren't doing this because we are fundamentally Frankensteinian,
No, I did not want to accuse you personally of it. And I didn't want to accuse scientists in general. And I think, look, we are all eating GMOs, every day, whether we want to or not, and it's feeding a lot of the world. And I'm simply saying that we do have so many capacities to change the world on such a fundamental level, and that's from the macro level of, blowing ourselves to smithereens and changing the atmosphere and changing the chemistry of the oceans to the micro level, that I sort of feel like all bets are off. I don't know where this is going.
So would you be, would it be more, I can tell you I would be, it's more satisfying, but would you be happier, because the debate for GMOs, I can give you the GMO debate.
Yes.
It's not a GMO versus, go and shop in Whole Foods debate, right?
Right, yep.
The debate for GMOs across the world is either GMO versus CMO, chemically modified organisms, which we've been using for the last, spraying insecticides, which dumps twice as much toxins in the oceans, et cetera. That's the reality. So
well, I'm going to push back on that, because a lot of GMOs are modified so we can put more chemicals on them. So that's a whole other.
Fair enough. So here's my question to you. I mean, do you think it's a complete pipe dream that we would, so going back to Wilson, is it a complete pipe dream that we would have hungry mouths to feed? Whether we could feed half of India without the high yielding varieties of rice is a question, or wheat is a question mark. I mean, should we, what's the other option? What's the middle road? Is the middle road that we make seed banks, and, or is there no middle road? Are we doomed down this road? Should we should we be CRISPRing things so that we restrain ourselves? I mean, that's also a possibility, right? We could use CRISPR as a police. We could be restraining ourselves in a variety of ways. I actually went to visit one of the seed banks. There are many now. Is there a middle road, or are we once we're driving down this road, it ends with monoculture or with people not being able to shop at Whole Paycheck for their.
Well, I think all these things, that question, I think, once again, you're like one humanities major's opinion, which is, to be honest, not worth that much, but I will offer it since I'm sitting up here. All these things are presupposing a kind of orderliness to the world. Is there a middle ground? Could we, use genetic modification to come up with some really, great crops, intensely farm certain areas of the world, leave other areas of the world unfarmed, and, get through to a moment when population starts to fall and blah, blah, blah? In theory, yes. Now look out in the chaos of the world today. We were having a conversation at dinner about what's going to happen in Brazil. We all know what's happening in the US of A. We could go down the list and say, okay, is that going to happen? So I bring to this, not a very high level of, just I think an ordinary American's level of skepticism about, we have to decide to do things. We cannot decide as a world that we should reduce carbon emissions, okay? Nothing could be simpler. That is the simplest, step. We have to reduce carbon emissions. That's like step one. We have technologies, very simple ones. They're called, windmills and solar cells, to start to make a dent in this problem, and we are not doing it. So the idea that we're going to come up with some great construct and, yes, it's theoretically possible. Do I think it's going to happen? I'm extremely skeptical.
Mm-hmm. Yeah, I think that makes a lot of sense. Okay, somebody says something like, a question, changing subjects a little bit, question for Sid. What about a fourth scenario? We are already immortal, perhaps life is truly eternal, but in a different form. Not sure I understand the question very well. Perhaps you mean that life just reinvents itself as time goes by, like the theory of evolution? I don't know.
I have no clue.
Okay. There's another one. Which
maybe it was a spiritual question.
Yes.
Maybe.
Yes. Yes,
possibly.
I think so too, yes.
Well, but so here's a comment about this whole transhumanist idea, which is if you really take it to the extreme, the real extreme transhumanism is to get rid of the flesh altogether, is to become information that can basically just keep going from machine to machine, or eventually not even in any machine altogether. So isn't this just reinventing the soul? Right, in modern technological terms, right? Because you just get rid of the flesh. The flesh is a problem. Look at all this mess we have to do, right? Cut genes here and all that stuff to try to get to, and if you get rid of it, all you have is information. If that's really true, then here we are. We just transport ourselves immaterially across time. So there is a huge religious component at the core of this transhumanist movement. Lots of scientists don't obviously think like that, but I think it's there for a lot of people that actually believe in it and want to feel it. Now, something more for you guys. Well, I also wrote books, but as authors of books, you are immortal. Your books, your words now live forever. How do you feel about it? I won't answer that. That's for you guys.
Go ahead.
I mean, I wish I had not put the word with in page 66 of just making it up. Well, I don't know, Elizabeth, what do you feel?
I mean, let's put it another way. Why do you feel compelled to write books?
Wow. I'm not sure I do feel compelled to write books. It's kind of a torment to write books. And when you write a book, I would, for myself, I write a book, there's a certain satisfaction when you're done after the torment, and you are hoping to put something out into the world in a package, that you hope that people that will, make them think differently. I guess that's what I hope for, and I'm sure also to a certain extent what Sid hopes for. And as for immortality, to me, I look around. I live in a college town. I look around the infinite number of books that have been sitting there and not taken out for generations. So I'm not sure that that's really a good way to achieve immortality.
In my case, I have a very simple formula or a thought about why to write anything. I think everything should raise a question or ask a question. My two books are, well, three books, but two of the bigger books are very much directed by individual questions. The first book, The Emperor of All Maladies, came about because a patient asked me a question. She said, I was giving her chemotherapy, and she said, where are we going with all of this? And you can take that question at face value, or you can ask the question, where are we going? I mean, this is an illness that is, redefined. Cancer has redefined our relationship to disease, so much so that we no longer use society as a lens to view cancer. We use cancer as a lens to view society. That much influence on our perception of ourselves, our perception of our future, and perception of our mortality. And yet we had no history, no roadmap for that. In the gene, I raise a question about who are we, and what are the limits of and how what we change. And I think in general, that's been my approach to this. A book I think is successful. I mean, Elizabeth's book, which I devoured, by the way, Sixth Extinction, asks a question. It's a book that raises a question and tries to offer an answer to a question. Those to me are fun, and even fiction does that. I mean, my wife's a sculptor. Whenever I come up to a sculpture, I say to her, well, she asks me once in a while, I'll go to the studio and she'll say, well, tell me about what you think about this work. And I'll say, the first thing I'll always say is, what question is this piece trying to answer? What question is this painting trying to answer? Every painting, everything in my lens, may not be your lens, but in my lens is about what question is this trying to solve? What is it trying to solve? What is it trying to raise? And it's a one way of viewing the world. It's a way of viewing the world in which everything is driven by a series of questions.
Yeah. So in the end of the day, I guess we're meaning-seeking creatures. And we do the things we do because we have the urge to engage with these, right?
Right.
And that's what makes you not completely whole, but at least more whole, right? Okay, so there's one last question that I want, and then we'll close. On soft immortality. In some sense, we're already living it. And this is the numbers here. I don't know, 50 billion cells from your body die every year. Is that correct? 50 billion?
It's 52, but
okay.
Oh, no.
Our bodies days ago are different from today's. And that's an interesting question, right? Where is the blueprint?
This is the Delphic boat question, right? So
yeah.
the famous conundrum, which has been raised many times by philosophers since a long time. If you have a boat and you replace every plank in the boat, is the boat still a boat? This actually is a question that has very much to do with things that you're thinking about too. The question you raised about identity. Mm-hmm. If you recreate the planet and repopulate it with everything that we ever saw,
would it be the same planet?
Would it be the same planet?
Right.
And this is a very fundamental philosophical question. I'm not sure I have a single kind of answer to that, but the point is that the fundamental difference is the difference in autonomy. So, and again, this goes into some things that we've been thinking about as biologists for a while. Why is the body a body? And it's a Delphic boat question. If your cells are being replaced all the time, why is a human body a single body? It's a Delphic boat. Where the question begins to become interesting is your body remains a body because it has autonomy. It is servicing yourself. It is in service of something. When you necessarily create a clone, and this again, there are many parallels to the planet here. When you make a clone, that clone assumes autonomy of itself. If there was a war between you and your clone, the clone would side for itself. And it would say, go take your GoPro memories and I'll tell you where to put them. And this may indeed be the case if we want to do this version of immortality, or this version, even if we take transhumanism to the nth extent as information movement, what is there not to say that at the third generation, this machine will say, I'm not interested in your memories.
Yep.
Go take your memories. I want my new ones. And we would end up being right back to, ironically, where we are now. When our children say, I'll tell you what to do with, with your recommendation to read War and Peace, Daddy. So there is, of course, obviously these are deeper questions, but they go back, not the metaphors extend across human beings into planets and ecosystems as well.
Yeah. Okay, well, just one last thing that I wanted to say, that you can be sure that given modern astronomy, there's only one planet Earth in the whole universe. There may be other planets that could be somewhat similar, but no planet will have the same history as our planet. So this is the only Earth that exists. And furthermore, there are no other humans in the whole universe. There may be humanoids out there. Who knows? We have no clue. But there is only one species like our own, because we are the product of the history, a very specific contingent history of our planet. So we are very special in the end of the day, us and the planet. So let's do something to protect it. Thank you.
Thank you.